Recently, I came out with a video where I showed you exactly what steps you want to go through in order to solve an optimization problem. Well, in today's video, I wanted to show you an example of how to actually solve one using these steps. If you want to go check out that video where I went in depth in the actual steps themselves and gave you kind of a guide that you could use on your own, just go click up there or over there. But if you want to see an example of how to actually apply these steps, you're in the right place. So be sure to stick around to the end of the video. I'll be showing you kind of a brief overview of these steps again, and then showing you exactly how to actually apply them based on a specific example. I think you're going to get a lot of use out of this video too. But without further ado, let's go ahead and jump into the example and I'll show you exactly what I'm talking about. A box with a square base and an open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. Okay, so like I said, first thing you want to do is draw the situation. We have a box, we know it has a square base, so we're trying to draw a box with a square base, and it has an open top. Okay, so it doesn't need to be a great drawing. You don't have to be Picasso to, draw a good drawing of your box here. We just need some passable box. So we're going to get a box type shape here. Okay. And we know that we have an open top here. So this is a bit of a harder thing to show in a drawing, but we do want to keep in mind that the top is open. So we don't have to worry about basically the cardboard that's going to be needed to fill in the top of the box because the top is open. So all we really need to kind of think about here is the cardboard that we need to build basically the four sides of the box and the bottom of the box. Okay, so we don't have to worry about this red face, the top of the box. We can ignore that. But what we want to do at this point is label our drawing, like I said. So let's just go ahead and say that we're going to, keep in mind, we know that our box has to have a certain volume, but that means that volume is not the quantity that we're trying to optimize, right? The quantity that we're trying to optimize, which means find the maximum or minimum of, is the amount of material used. So the amount of material needed to construct the box is basically the surface area, the amount of cardboard we need to build these four sides and this bottom. So what we want to actually optimize is surface area. So I'm just going to go ahead and call that S. Actually, I'm going to call it SA because S sometimes looks like a 5 when it's by itself. So I'm going to say SA is our surface area, and we need to come up with an equation for this. So again, what we're going to have to kind of use here, what we have to figure out at this point is what are the other measurements that we have to use to find the surface area. Well, it is a box. We're probably going to want to use the length, width, and height of the box to find its surface area. Okay, so in general, surface area is going to use the length, width, and height. However, there's one other key piece here that this problem told us that we can use to simplify this a little bit further. Because if we were to go straight to surface area from here, using length, width, and height, we end up with a 3-variable equation. However, notice it says right here, we have a square base. What does that mean? That means that the length and the width are going to be equal. In order to have a square base, we need this side right here and this side right here to be the same length. That is going to create a square on the bottom. So instead of thinking of length, width, and height, we can actually just eliminate one of these letters since we know that they're going to be equal to each other. We know that this side length is going to be the same as this side length, which is also the same as this one here and this one. So all four of these sides down here at the bottom are going to be W. So now to find the surface area of this box, let's think about this box has 5 faces, right? We have the 4 sides and the bottom. We don't have a top. So the surface area is going to be the sum of all of the areas of these 4 rectangles and the square base. So the square base is going to have an area of W times W, so W squared. And then each of the 4 sides of this rectangle is going to have an area of H times W, right? Because it's just a rectangle. Height times width is going to give us the area of that. So we're going to have plus W times H Now that's just one of the four sides. We have four of these sides. So 4 times W times H is going to be the total surface area of this whole box. And again, we don't have a top, so we don't have to worry about that face. So these 5 faces are going to add up to this surface area. So this is the equation that we need to optimize. Okay, so then the next step was to come up with our restriction equation. What does this problem tell us about how these different quantities have to be related to each other? Well, this is pretty much the only restricting information we have. We know that the volume of the box has to be 32,000 cubic centimeters. So what that tells us is the volume of this box, the volume has to be 32,000 cubic centimeters. What is the equation for the volume of a rectangular prism? It's length times width times height, right? So the length and width and height of this box are H, W, and W. So the volume of this box in particular is going to be H times W, which is the same as H times W squared. So we know this is the volume of this particular box. So let's just call this volume of this box volume 0, volume naught. What we know is that the volume of this box, this V0, has to be 32,000. So we know that 32,000 equals H times W squared. Okay, so now we have our restriction equation. We have the equation we need to optimize. So now what we can do is we can use our restriction equation, solve for one of the variables. Doesn't really matter which one you pick. Let's just go ahead and solve for H. To solve our restriction equation for H, we would just have to divide both sides by W squared. And that would give us H equals 32,000 over W squared. Okay, so now what we can do, since we know this quantity here is equal to H, we can go back up to the equation that we are trying to optimize, the surface area, and we can replace our H with this quantity here, 32,000 over W squared. If we do that, we find out that our surface area is going to be W squared, which we already had here, plus 4 times W times 32,000 over W squared. So plus 4 times W times 32,000 over W squared. Okay, now let's just take a moment to simplify this equation. So simplifying this, that W is going to cancel with one of those W's, just giving us a W there. So we're going to have W squared plus 4 times 32,000, which would give us 128,000 over W. Yeah, because 30,000 times 4 would be 120,000 plus 8,000. Okay, perfect. So now this is going to be our surface area. And now look what we have. We have an equation for our surface area, which is the thing that we're trying to minimize. And we have it just in terms of W. It's a single variable equation at this point. So now once we've done that, we can move on to finding the actual absolute minimum of this equation. So to find the absolute minimum of an equation, first we need to find its derivative. So we're going to find the derivative, we'll call it SA prime. Before we do that though, let's think about how we can rewrite this equation, because having something over W doesn't make it very easy to find the derivative of that function. So instead, what I'm going to do is write this as 128,000 times W to the negative 1 power, because W to the negative 1 is the same as dividing by W. So now to find the derivative of this function, we can just use the power rule. Power rule says we're going to bring this 2 down in front and then minus 1 from the power. So that's going to give us 2W to the first is just 2W. And then again, power rule here says we bring our power down in front, multiply it by the coefficient. So instead of plus 128,000, we are now going to have minus 128,000. And then keep our base W as W, and then minus 1 from the power. Minus 1 is minus 2. Okay? Now I'm just going to put this back into a fraction because the next step is going to be easier with it not being in a negative power. And then what we need to do in order to actually find our critical numbers, the places where our absolute minimum might occur, is by taking our derivative and setting it equal to 0. Okay. We also, in general, to find critical numbers, need to consider where our derivative would not exist. Looking at this function, there's only one place where we need to, or one thing that could happen, I should say. Actually, yeah, one thing, sorry, that could cause this derivative to not exist. And that is if the denominator of this fraction equals 0. Because if that happened, we would be dividing by 0, which is not okay. You can't do that. The only thing that would cause this denominator, w squared, to equal 0 is if w equals 0, which if we go back up to our drawing, w equaling 0 does not make sense because the width of our box would be 0. We would not have a box. So we can ignore w equals 0 because that's not even within the domain of what w can be. So you always want to be careful to think back to the real world example of what this equation represents and make sure that you're plugging in numbers that actually make sense based on the situation. W equals 0 makes no sense. And that's the only place where this derivative, SA prime, would not exist. So we only need to worry about where does SA prime equal 0. So we can solve this equation for W to find that critical number or critical numbers. So first thing we'll do, we'll add 128,000 over W squared to both sides. Okay, then we can multiply both sides by W squared so that we can get rid of our fraction and just have everything on one line, basically. So that's going to give us 128,000 to W cubed, divide by 2. And that should give us 64,000 equals W cubed. And then we can take the cube root of both sides, giving us W equals the cube root of 64,000, which you can just plug into a calculator. However, I believe, no, that might not be a cube number. But anyway, whatever this number ends up being, the cube root of 64,000 is going to be the W that gives us our critical number, which is going to have to be, typically what you would probably want to do from here is confirm that that is an absolute minimum. Based on the context of the problem, that critical number should be an absolute minimum. There shouldn't just be one critical number that creates a situation where we're using the most possible cardboard to make this box. It doesn't really make sense. So we can just go ahead and assume that the width of the cube root of 64,000 should be the place where we minimize the amount of material used to make a box of this volume. Now, do keep in mind units. This is in cubic centimeters, so this is going to have to be in centimeters. So the units here are going to be centimeters, and that should be the width that gives it to us. So keep in mind, we do want to find the dimensions of the box. We're not quite done yet just because of what the problem is asking us to find. They want us to find the full dimensions. Well, we found this equation here, H equals 32,000 over W squared. So we know our W, so we know the length of the base of each of these sides here. We know that those are both going to be the cube root of 64,000. Then to find the height, all we would have to do is plug the cube root of 64,000 in for W here. So that would give us 32,000 over the cube root of 64,000 squared. And this is going to be the height of our box. And then the width and length of our box is just the cube root of 64,000. So I'll let you plug those into a calculator to get your actual final number there. I think it'd be fine to leave this in exact form, assuming that 64,000 is not a cubic number. And if that's the case, then I think this is a perfectly fine answer. You could probably do a little more simplification from there, but I'm not going to do that. I'll leave that for you. Hey, you made it to the end of the video. Thanks for sticking around to the end. I hope you got some value out of that one, and I'm guessing you did if you stuck around this long. If that's the case, go hit that subscribe button down below, and that bell icon too, because if you like this video, you're going to like a lot of my other videos too, and I'm going to provide you with a bunch of value so you can keep crushing it all term long and get better grades in calculus. If you like better grades, hit that subscribe button. And if you want to keep that brain train rolling, go click on one of those videos over there, and I'll see you next time. Thanks.